In part 10, we're going to talk about what happens when shader graph doesn't have a node for something we want to do. You'll remember back in part 7, we made a basic cell shaded effect which uses the main light direction node, but this immediately exposes two limitations. Firstly, there is only a node for the direction, but lights are defined by more information than just their direction. They have colour, and for some types of light, such as point lights, the light intensity falls as the distance between the light and the surface being illuminated increases. Second, this only gets us information about the primary light in the scene. If you have objects lit by a main directional light plus some point lights, then sadly those additional lights won't have an effect. We're going to solve both of these issues. First, copy the cell shaded graph from part 7 and name the duplicate cell shaded additional, or you can just edit the original directly if you want. Here, the main lighting calculation was taking the dot product between the light direction and the normal vector. I want to add support for extra light data such as colour, which requires us to write some custom HLSL code in a separate file and use a custom function node to include that code in our graph. Or you can just copy this file from the GitHub repository I've linked in the description and sort of skim your way through me explaining it. This isn't an HLSL tutorial per se, but I'll at least explain what these functions do broadly. First, we need to create an HLSL file, which is more annoying than it ought to be. There's no way to do this with the Create menu, so you'll need to create an empty file in something like Visual Studio, then save it with the HLSL extension. I named my file customlighting.hlsl. The file is wrapped by a header guard called additional light included, which prevents Unity from trying to include your functions in the generated code more than once. Inside this file, we can define as many functions as we want, and then the custom function node can choose any one of those functions by name. Each function needs to be written in a very particular way. To get data from the main light, my function will have a return type of void. Its name is mainLight, and then I need to add either _float or _half to the end of the name. That's because graphs can use numbers with either single or half precision, and this is something you can actually choose between on the graph level in the graph settings, or on individual nodes in the node settings. But to be honest, you will rarely need to think about this, at least as a beginner. Yes, half precision numbers will be slightly more efficient at the expense of precision, but the savings will be tiny. You can include both _float and _half versions of the same function in your file, and I will include both versions on the GitHub though. Next, we put all the inputs and outputs to the function in its parameter list. We need the world position as an input, and then as outputs, which we specify with the out keyword, we'll have the direction, color, and attenuation factor. That last one is a value between 0 and 1, where 0 means the light's too far away, so the object is not lit, and 1 means the object is fully lit by this light. The code inside the function differs depending on whether it's running inside a shader graph preview window or in a real scene. With #ifdef shadergraph _preview, there is no actual light, so we'll just fake one with a constant direction and a white color. Else we'll get the real main light using the getMainLight function. If you're interested, this function can be found in URP shader library in the lighting file, which you can freely open by scrolling down the Packages section of the project view and going to Universal RP Shader Library. These are the include files that are used by URP shaders, and you can include them in your own code shaders if you want. There's a few more in the core RP library shader library too. I found them really useful when designing my own shader asset packs, but now we're straying a little from shader graph. Basically, the lighting file is one that shader graph includes anyway, so we can use getMainLight from it, and then set the output values accordingly. So that's the mainLight HLSL function done, and now we can use it in shader graph with a custom function node. When we click on the node, we'll need to first drag the customlighting.hlsl file into the source slot, then type mainLight into the name field. Don't include the _float bit of the name here. It's going to throw up an error, and that's because we haven't set up the inputs and outputs yet. We can do that by clicking the plus arrow buttons, and then we can add each input or output as it appears in the code. WorldPos is a vector 3 input, and then direction and color are both vector-free outputs, and finally, attenuation is a float output. We can rename each one by double-clicking the name field. Once you've added them all, the node will stop displaying errors and will appear a different color depending on the fake direction we specified in the shader graph preview part of the code. Now, instead of using the main light direction node, we can use our custom function node and input a position node in world space to it. Currently, our graph will do the same thing as before, which is a good sanity check to see if our code works. However, the point of using this custom code was to incorporate the light color and attenuation into the mix. So I'm going to take the result of the ambient light lerp node and multiply by the light color, then by the light attenuation. And now, in the scene view, we can change the color of the main light and see the color of the mesh change too. Of course, we're still only taking the main light into account. To get information about additional lights, such as extra point lights around the object, we need a bit more custom code. I'll write a second function called additional light, which will take the same parameters as main light, plus a light ID integer to specify which light we want data about. In the code for this function, I'll set up a fake light, which is completely black and fully attenuated. Then I'll say, if this code isn't running in a shader graph preview window, and if the light ID is lower than the total number of additional lights shining on this object, we can grab the actual additional light information and output that. Let's add another custom function node and set it up similar to the one for main light. We'll need to drag the custom lighting file onto the source slot again, but this time, the function name is additional light. For the inputs, we have a vector3 called worldpos and a float called lightID. There isn't a separate option for an int, so a float will do. Then the outputs are the same as the ones from main light. A vector3 called direction, a vector3 called color, and a float called attenuation. And now we're going to come up against what I think is one of the biggest and most impactful limitations of shader graph. It can't do loops. In shader code, we can loop over each additional light once and run the same bit of code for each. But in shader graph, not only do we need to duplicate the nodes to run the calculations for each light, we also can't dynamically check how many lights actually exist and only run the code for that number of lights. I'll explore an alternative method later, but for now, I'm going to assume there are 4 additional lights and accept that my graph wastes some performance if there are actually fewer than that. We can use a similar set of nodes here for the lighting calculations as we previously used for the main light, so I'll speed through this. First, I'll input the world position to my additional light node and leave the light ID as 0. Then I'll take the dot product of the additional light direction with the normal vector, then smooth step the output of this using the cutoff thresholds, and then we can multiply that result by the additional light color, and then its attenuation. The only difference here is that we took the ambient light into account in the main light calculations, but that only needs doing once. We can then add both lighting values together. To make sure my graph doesn't become totally cluttered, I'll turn this section of nodes into a subgraph. Let's select the nodes starting with the additional light node and ending at the last multiply, then right-click and choose Convert to Subgraph. Opening up the subgraph, let's tidy things up a bit. I don't need the vector3 property, so we can delete that, and instead use a position node in world space for the additional light node. We do need a property for the light ID, however, so I will add a float property called light ID and connect it to the additional light node. Finally, our singular output is going to be the color of the light after attenuation has been applied, so we can rename this output to light color or something similar. Back on the cel-shaded additional graph, we now have a single node doing all of the calculations for the first additional light, and we can duplicate this 3 or more times. Change the light IDs of the new nodes to 1, 2, and 3 respectively, and add together the outputs of all of these nodes to the lighting calculations for the main light. If we save asset and return to the scene view, we can verify that everything's working by adding 4 point lights around the object and moving them. Adding a 5th point light means that one of the lights gets ignored, although I'm not sure exactly how Unity decides which of the 4 lights are the closest. It seems a bit wonky sometimes. Now, as I mentioned, this method might be a bit wasteful if there are fewer than 4 additional lights, because it's still running the calculations and always coming up with a black light color for those phantom lights that don't exist. We might even have more than 4 additional lights, so we could extend the graph with more nodes, but that makes the first problem even worse. Point is, this method is not easily scalable. To that end, I've included another HLSL function called AllAdditionalLights, which takes in the world position, the world normal, and the cutoff thresholds, and outputs only a light color. And it just does all of the additional light calculations right here in the HLSL, taking advantage of looping. You'll recognize the names of HLSL's built-in functions here as being the same as ShaderGraph's nodes. Putting everything together in ShaderGraph is the same process of adding a custom function node, dragging in the custom lighting file, and inputting all additional lights as their name. Then matching up the inputs and outputs to those in the HLSL code and inputting the required nodes into the custom function node. Replacing the individual additional light nodes from before, then we can admire the fact that the graph is far simpler with just one node handling all of the additional light calculations, and hit save asset before returning to the scene view, where we can add additional lights up to the maximum limit of 8, and all of them will have a visible impact on the object, while doing only the exact number of calculations needed for however many lights we actually have. So why did I choose to make this graph in this tutorial? Well, I think it's a use case that ShaderGraph does not handle well for a few reasons, primarily the lack of lighting nodes and the lack of loops. As much as I hate to admit it, you might sometimes find things far easier to work with in code, even if you're a beginner. So it's still worth your time to pick up a bit of HLSL, even if you plan to mostly work inside ShaderGraph. It's at least worth knowing what to search if you do need to implement a custom node. That said, I think this is one of the more challenging scenarios for ShaderGraph, and we were still able to put together the effect we wanted, even if it's a bit messy. Thanks for watching, and if you learned something, I would really appreciate if you checked out my Patreon or my premium shader asset packs. I'd love to make tutorials like these forever, and the best way to make that possible is to buy stuff off me so I can afford to eat. I recently released PSX Shaders Pro on it. It's a pack of shaders designed to look just like the PS1, including its limited vertex precision, wobbly perspective incorrect textures, and a CRT post-processing effect. It should hopefully land on the asset store soon too. The basic series will continue, and until next time, have fun making shaders.